So let's look at a problem. So this is combined capacitor circuits. So let's say we have 3 capacitors connected to a battery. Okay, so we have C1, C2 and C3, and the battery has EMF of 1.5 volts. So in this problem we want to find C equivalent of all these 3 capacitors, okay, and we want to find charge in each of the capacitors, Q1, Q2 and Q3, and we want to find delta V in each of the capacitors, delta V1, delta V2, delta V3, and we also want to find the energy stored in each of the capacitors, because the function of capacitor is to store the energy. So we will find energy stored in first one, energy stored in the second one, energy stored in the third one. Okay, so we'll find those quantities. So first thing is we want to find the equivalent capacitors. So we want to see which ones are in series and which ones are in parallel. So usually it's always better idea to start from the right side. Okay, if you choose these two, then these are neither in parallel nor in series. Okay, for them to be in series, there shouldn't be anything in between. Okay, so they should be like this, then they are in series. Okay, and in order for them to be in parallel, both the ends should be connected. So this end is connected, end to end is connected, but this side of the end is, there is a third capacitor here, so they are not connected end to end here. There shouldn't be anything in between. Okay, so that means they are neither in series nor in parallel. So that means we need to always start from, it's better to start from the right side. Okay, so these two are in series, okay, because there is nothing in between here. That means they are in series. So when they are in series, we can find the equivalent capacitance by using the reciprocal formula. We can replace the 2 capacitors by their equivalent capacitor. So you can place the equivalent capacitor anywhere between this part, okay, anywhere, wherever you like. So let's put it here. So this would be C equivalent of those 2. So let's write C23. So we want to find C23. We can use the reciprocal formula for series capacitors. So 1 over C2 plus 1 over C3. Okay. So the value of capacitors are given. Okay. So C1 is 330 microfarad. C2 is 10 microfarad. And C3 is 47 microfarad. Okay, so C2 is 10 microfarad and C3 is 47 microfarad. So you can do the calculation. So in your calculator, you divide 1 by that number, and then 1 by 47, and then add those two numbers. So when you do the calculation on the right side, that would be 1 over C23. Okay, but we want to get C23, okay, not the reciprocal. So if you do the calculation, you get C23 to be equal to 8.25 microfarad. Okay, that's what you will get. So this C23 is 8.25 microfarad. And now we clearly see here C1 and this C23 are in parallel. Okay, so the end to ends are connected. There is nothing in between. So these two ends are, this end and this end are connected. There is nothing in between. This end and this end are connected, so there is nothing in between. That means they are parallel. So we can write the equivalent capacitance So we can replace these two by a single capacitor, and you can place it anywhere in between, okay, anywhere here. So this is still 1.5. So now let's call this C1, 2, 3. Okay, so that's the equivalent of these two. And when the capacitors are in parallel, we use this formula. So C1, 2, 3 is given by C1 plus C2, 3. C1 is 330 microfarad plus C2, 3 is 8.25 microfarad, and if you add that, you get 338.25 microfarad. Okay. So we got the C equivalent, 338.25 microfarad. That's the answer for the first one. Now next is we want to find the charge and potential difference and energy in each of the capacitors. So for that, we'll start with this equivalent one. So just like in the resistors, when the capacitors are in series, they have same charge, okay, not current. Here we don't talk about the current. In capacitance or capacitors, we talk about charge. So if you have, let's put this in a box. If you have two capacitors in series, if you have Q1 on this one, you will have Q1 on this one also. Okay. If you have another one, you'll have Q1 on that one. So same charge if they are in series. And if the capacitors are in parallel, then they will have same potential difference, delta V, delta V, delta V, okay, same delta V. So again, instead of current, we deal with charge in case of capacitors, because capacitors store charge. So let's find the charge in this capacitor. We have this formula. Now, in resistors, we used Ohm's law, but here we don't use Ohm's law. Okay, we use this formula. So Q is equal to C times delta V. This is the formula we used for the capacitor. So we will be finding the charge on C123, so we'll use C123 here. And when you have only single component here and nothing in between, whatever potential difference you are using in the battery, the same potential difference will also appear on this side. Okay? So if you have 1.5 here, this will also have 1.5 volt because they are parallel. So C123 is 338.25 microfarad. Delta V 1.5 volts. So you need to convert this to farad. So you need to do times 10 to negative 6. That will give you farad. If you do that, that will give you let's see. Okay, you get some value here. Okay, I don't know. Can you guys? Actually, we don't even need this one, but I want to just find it to see if we may need that later. But we won't need this value. Okay, I will show you why. But let's find it out anyway. 5.707 times 10 to negative 4.
Yes, sir.
So that's Coulomb. Okay. So now we need to go backwards. So let's see. Let's use different color here. So this one is the combination of these two. Okay. And that means they will have, because this one is combination of the two parallel capacitors, so they will have same potential difference. Whatever potential difference you see in this one, the same potential will be on this one and this one, because they are all parallel. Okay, so this one will have 1.5 volt, and this one will also have 1.5 volt. Okay, that's what we said here. So whenever the things are in parallel, they have same potential difference. Okay, so let's find the charge in this C1. So charge in C1, let's call it Q1. Okay. So Q1 is C1, charge is capacitance times delta V. Capacitance in the first one, of the first one, what is that? 330 microfarad. So this is 330 microfarad. Changing that to farad, multiply that by 10 to negative 6 farad. Okay, that's C1. Delta V1, it's 1.5. Okay, that's 1.5, and that gives you Q1, which comes out to be 495 microcoulomb. 495 microcoulomb. Likewise, we can find charge on 2,3. Okay, charge on this one, charge Q3. Capacitance, charge is capacitance times delta V. Capacitance 8.25, C23, okay, that's that. Microfarad, 10 to negative 6th farad. Delta V is, again, it's 1.5 volts. Okay, so when you do that calculation, you get 12,375 microcoulomb. Okay. Actually, you don't need to convert this to farad. You can just leave it micro because I'm using microfarad here. Okay, so I mean, if you want to express this in terms of 10 to negative 6, you can do that. What I mean is you can express this also as, okay, 495 times 10 to negative 6 farad, or you can express like that. You can write this as 12.375 times 10 to negative 6 farad. Okay, that's coulomb, sorry, not farad. The unit for charge is coulomb, sorry, not farad. Okay. Okay, so we got that. Now we need to go one step up. Okay. So we got charge on this one, Q1, and charge on that one. So we want to go one step up. So these two combine to form this one. Okay, so this, they are in series and they combine to form that. That means whatever charge you have here, the same charge will also be on the constituent ones. Okay, so the charge you have here, Q23, is 12.375. So they will have 12.375 microcoulomb. This one also have 12.375 microcoulomb. Okay, so they have same charge. And then once you have charge, now you can find delta V for each of these ones. So delta V2 would be using this formula, Q is equal to C delta V. You can get delta V is Q over C. So Q is 12.375 microcoulomb. C2 is 10 microfarad. You can cancel micro and micro. Okay, and that will give us 1.24, or no, not 1.24. 1.237. So rounding off 1.24 volt. Okay. So here also you do the same thing. Delta V3 would be Q3 is 12.375 microfarad or microcoulomb. Charge over capacitance. Capacitance of C3 is 47 microfarad. So that gives us 0.26 volts. Okay. So we got everything except the energy. Okay. So we need to find energy stored. So you can put all these values in a table just to make it a little bit more clear. So let's put everything in table. So let's put capacitors on this column. So we have 3 capacitors. C1 is 330 microfarad, C2 is 10 microfarad, and C3 is 47 microfarad. Okay, and then let's write column on this one, Q on this one, delta V on this column, and then energy on this column. Okay, so Q on C1, what did we get for Q on C1? So Q2 is that, okay, Q2 on C2 is 12.375 microcoulomb, okay, that's that. Q3, same thing, 12.375 microcoulomb. And then on Q1, let's see what we got. Can you guys tell me what you got for Q1? We found that somewhere down here.
Q1?
Mm-hmm.
495.
Yeah, so 495 microcoulomb. So 495 microcoulomb. And then delta V across that is 1.5. Okay. Delta V across C2 is that 1.25, 1.24, sorry. And then delta V across C3 is that 0.26 volts. Okay, now energy, to find energy we have this formula, U is 1/2 C delta V squared. Okay. You can use this formula, or we also have, you can also use this a little bit differently. So C delta V is Q over C, so Q over C squared. So you see here delta V, we have Q is C times delta V. We can substitute delta V by Q over C. Okay, so instead of delta V we can write Q over C. So then if we simplify that, we get Q over C squared. Okay, so you can use either this one or that one, whichever you want. Okay. C delta V. So you substitute these values in this expression, and then you get this one to be 371.3 joules. This one is 7.69 joules, 1.59 joules. Okay, again this is using that formula. So then you should be able to do the, once you do this, you should be able to do the question from the worksheet. It's similar kind of question. I think I showed half of this last time. So this is the worksheet question. It's same thing as the one I just showed. You need to find charge, voltage, and energy stored in each of the capacitors. Okay, so let me just give you a little bit of hint here. See. Okay, so in this one, you combine these two, okay, using this formula. So C equivalent of 1 and 2 would be 1 over C1 plus 1 over C2. So this is the formula for capacitors in series, which is just opposite to the formula for resistors in series. So in case of resistors, you just add them, okay? But in capacitors, you use this. So the thing you get here would be reciprocal of that. You need to do the reciprocal thing, okay? That's always something you need to remember. And then once you have the equivalent one, so this one means there is a battery here, okay? So you can replace this by battery. So this voltage across A and B means it's connected to some battery. So this one is equivalent capacitor of 1 and 2. This one is C3, this one is C4, okay? And then in the next step, you combine these two. They are in parallel, so you use this formula. So C1, 2, 3, combination of these two would be C1, 2, 3 plus C3, okay? So add the individual capacitors. And by doing that, you get a single capacitor. Okay, you have a battery here. So this one is C1, 2, 3, and this one is C4. Now these two are in series. So to get the equivalent of that, you use C1, 2, 3, 4 is 1 over C1, 2, 3 plus 1 over C4. Okay? And then it's all about applying this formula. So formula for capacitor, Q is C delta V, apply that. And also apply this rule. If the capacitors are in series, Q same. If they are in parallel, delta V same. Okay. So that's all you need to do. And for energy, you use 1 over C delta V squared, or 1 over Q squared over C. Okay, you should be able to do this one after I showed you the other one. Okay, let's look at the worksheet I gave you. So in the worksheet, we have combination of a capacitor and a resistor. So we worked on capacitor separately and resistor separately. Now we want to combine those two things in a same circuit. Okay? We have a capacitor that has capacitance of C, and we have a resistor that has the resistance of R, and they are connected to a battery. So the battery has voltage of E, okay, EMF. So first question is, it is asking, assign the correct signs to the capacitor, resistor, and battery. So let's assign the signs. Which one will have positive and which one will have negative? We know that the longer side of the battery is positive, shorter side is negative. And the side that is connected to the negative of the battery gets negative sign. Okay? So, and the side that is connected to the battery, a positive side of the battery, gets positive sign. Okay? That's the rule. And we know that the capacitor has two plates. If this one is positive, then the other side would be negative. Okay, so this would be negative. And the side that is connected to this negative part will be negative here. No, sorry. This would be positive here, sorry. So, no, for this one, let's see. Okay, so for resistor, we need to use this notion. Okay, so let me take it back. For resistor, capacitor is fine. I want to erase that one. Okay, I cannot do that for resistor. So let me use this notion here. So capacitor is fine. So the positive side connects to positive, and the side connected to negative becomes negative. Okay, for this one, see which way the current is flowing. Okay, so current, we are talking about the conventional current here. Conventional current is, it flows from positive to negative. Okay, we use this convention. That means the current is flowing this way. Okay, going out from positive side of the battery, and then entering to the negative side. The current always comes out of the positive and enters to the negative. That's what we use. That means in this resistor, current is flowing this way. Okay? That means this is the entry point, and that's the exit point. And we know entry point is positive and exit point is negative. Okay, that's what we used last time. So we got the signs for all the components. Now let's look at the second question. Write the Kickoffs rule for the circuit. So let's write the Kickoffs rule. So when we write the Kickoffs rule, we first need to choose a loop, either clockwise loop or counterclockwise loop, whichever you want. So let me choose a loop, means a path. Okay, we are just following some path. So let's follow this counterclockwise path. Okay, loop means a path. I'm choosing this counterclockwise path. And then start with some component. Let's start with this C. So for C, we are going from positive to negative. Okay, from positive to negative. We are going this way, counterclockwise. Now we want to apply loop rule. That's what the question is. What is the loop rule? Loop rule is sum of all the potential difference in a loop is 0. Okay, that's the loop rule. So what's the potential difference in this capacitor? We are considering this capacitor. That's our first component. We know this formula, Q is equal to C times delta V. So the potential difference across this capacitor would be Q over C. Okay. So that means the potential difference here is Q over C. Okay. And we are going from higher potential to lower potential. And higher to lower means we have a negative sign. Okay, that's what we used last time. So when you are going down the hill from higher to lower potential, you lose the potential. That means you need to put negative sign. Negative means you're losing the potential. Next component is this resistor. Okay. And what's the potential difference across the resistor? It's negative. Sign is negative. That's right. We are going downhill from positive to negative. But what's the expression? Potential difference across a resistor. Ohm's law, right? I times R. This is for the resistor, and that's for the capacitor. Now we don't have I here, so let's just assume that the I in this circuit is I. Okay, the current is just I. Consider it's I, and it's same everywhere because it's series circuit. In series, current is same everywhere. So delta V across R is I times R. Okay. And then we have another component, this battery. And the potential difference across the battery is E. We are denoting that by E. You can sometimes write delta V instead of E. They are same. What about the sign? We are going from lower to higher potential. We are going uphill. That means we are gaining the potential. So that's positive. Okay, gaining is positive. So that's the Kickoffs rule. Okay, that's the answer for number 2. Now we can write this, rewrite this equation, minus Q over C. This I, the definition of I is change in charge over some change in time. Okay, how much charge is flowing through some interval of time. That's the definition of current. So we can write this as I as delta Q over delta T. R is equal to 0. Okay, or you can write this as delta Q delta T R. I'm just multiplying both sides by negative sign just to make it a little bit more simpler. That plus Q over R, just multiplying all the terms by negative sign. Okay. So this kind of equation is called differential equation. Okay. If you take calculus based physics or some calculus course, you will solve these kinds of equation. But fortunately in this course we don't need to worry about differential equation. We don't need to solve that. Okay. I will just give you the solution for this. Okay. So this equation has this form of solution. So this equation basically gives you the charge that is being stored in this capacitor during different times. Okay. So the solution for this equation is given by potential difference times capacitance 1 minus E minus T RC. Okay. That's the solution. This is called differential equation. If you take some calculus course, you may need to solve these kind of things, but we don't need to worry about that here.
You said that E is the same thing as delta V?
Yes. So the difference is, let me tell you the difference. So let's say we have a battery. Okay. So let me tell you the difference between E and what is difference between E and delta V of the battery. So battery, let's say that's the picture of a battery. Okay. We have positive side here, negative side here. So there may be some internal resistance in the battery. Okay. So it's not only the source of potential difference, it also can consume some potential difference. Okay. What that means is it's providing some potential difference, but it has this little bit of resistance that is actually consuming that. Okay. If you do not consider that resistance, if you are considering without that drop, it's called this E. Okay. Electromotive force. But if you are considering that, it's called this delta V. Delta V is when there is some drop across that, you get a little bit less than what it is supposed to give. Okay. Let's say your battery says its delta V is 1.5. You may not get exactly 1.5 because there is some drop, a little bit of this loss in this small resistor. Okay. You may lose like 0.5 or something like that, or even less than that. Okay. So that's delta V. And E is the ideal one. Okay. What it is supposed to give if there is zero resistance. But we don't need to worry about those differences. Okay. We'll just call it same kind of quantity. So E and delta V are same. Okay, so the next, let's look at the next part of the question. So this equation, let me tell you this one first, and then we can answer that one. So this equation gives us or tells us how the charge is accumulating in the capacitor. As the time passes. So that's what this equation gives us. Okay. So at different times, how the charge is increasing or accumulating in the capacitor. So when you start the circuit in the very beginning, at the instant when you connect this circuit, let's say you have a switch here, okay. At the instant when you close the switch, the charge will start, the current will start to flow. In the very beginning, there is no current here, okay, zero current or zero charge. There is no charge. Okay, at t equal to 0, Q is 0. But as you close the switch, current starts to flow here. As the current flows, the charge starts to accumulate here. So initially you will have a little bit of charge, and then as the time passes, you will have more and more charge, more and more charge, more and more charge, more and more charge, until it becomes full. Okay. So eventually, when the time is infinity means after long time, Q would be maximum. Okay, you will have maximum charge. So that's what happens in the capacitor. So let's see. After charging the capacitor for a long time, it attains the maximum charge, which is when the time goes to infinity. Infinity means after a long time. So number 3, let's look at that. Find the expression for the maximum charge in the capacitor. So we want to find the expression for Q max, maximum charge. What would that be? So one thing we know, we get Q max when t is infinity. So we need to use this condition in this expression. Okay, we have this expression. Q max would be then EC. There's nothing changed in EC. E is constant. C is also constant. Nothing happens after a long time. 1 minus E. Now time goes to infinity. Okay. So when time goes to infinity, what happens to this expression? E to the very, very large minus very, very large number. Have you guys ever seen this kind of exponential terms in some other course? Never seen that? Huh? So there are two types of infinity exponential thing here. One is e to the minus thing and e to the plus. Okay. If you have this one, if the time goes to infinity, this term will go to infinity. It will be like that. Okay. After infinitely long time, it will go up at infinity. But this negative is it's dropping like that. So what will happen at infinitely long time? Huh?
It'll get closer and closer.
Yeah, it will be closer and closer to 0, right? It would be almost 0. So because we have negative sign here and our time is infinite here, that means this expression would be almost equal to 0. It would be very, very close to 0 value. So that means that means this thing would be, let me just erase. Let me just erase that. So this thing would be 0, okay, because ETRC, when t is 0, t is infinity, it goes to, it's almost 0. So that means Q max is E times C. That's the expression for maximum charge. So you are asked to find what is the maximum charge in the capacitor after a long time. What you do, you multiply the potential difference of the battery or EMF of the battery and the capacitance of the capacitor. Let's say we are using the capacitance here 10 microfarad and the battery has 1.5 volts. Then how much charge will there be after a long time? So Q max would be, just for this example, E is 1.5 volts and C is 10 times 10 to negative 6 coulomb. So that would give us 1.5 times 10 to, or 15 micro coulomb. Okay, so this would give us 15 microcoulomb. So we got that. Now number 5, which graph below represents the charging of capacitor as a function of time? Just think about that, okay? Just not mathematically, but think it conceptually. So think about how the charge is accumulating on the capacitor. So see which graph will match that. It cannot be second graph, because second graph shows charge is going down, because that's not what's happening here. Okay, charge starts from 0 and then it's climbing, it's going up. Okay, so you cannot have this second one. Third one also not true, because charge is not going down. We are accumulating the charge. So it's either first one or third one, first one or fourth one. So which one you think would be the right one? 4? 4 is, you are just accumulating the charge, okay? It's going up all the time. It goes to like infinity at the infinite long time. Is that true? The capacitor doesn't have infinite amount of capacity to hold the charge, okay? Or it cannot hold infinite amount of charge. It can hold only some limited amount of charge. So which one would be the right one then? 1, exactly. So 1. So it will start to charge. It will charge, and then after some time, it will plateau. Okay, it will be constant because it cannot hold any more than that. So what I mean is, so you start to charge. So that's the time axis. That's the charge. Initially, there is 0 charge. You start to charge. It reaches some maximum, and after it reaches maximum, it will just become flat. Okay. Okay, so I think we will continue the other parts next time. We are out of time.